So far we've been talking about thermodynamics. Now it's time to talk about kinetics. So each time I looked at those things and said they were spontaneous or they were not spontaneous, they favored the reactants, they favored the products, I was talking about thermodynamically. Spontaneity is not related to rate. So it's spontaneous for diamonds to degrade into graphite. That's a spontaneous reaction if you look up the thermodynamics. But it happens at such a very slow rate that we don't have to worry about all our diamonds turning into graphite anytime soon. So kinetics is going to be the study of rates. And it's what's going to tell us how fast a reaction occurs. So the rate of a reaction will be equal to K, which is a rate constant. It's specific for each reaction. Okay, the rate will be multiplied times the concentration of the reactants. And it does make sense that the rate is going to depend on how many reactants you have. They have to bump into each other. If there are not very many of them, the rate will be slower. If the concentration is higher, the concentration will be faster. So this is determined experimentally, this equation. And we have first order, second order, and third order reactions. In a first order reaction, if you have A plus B makes something, let's say it makes C. A first order reaction, the rate has, the amount of B has no effect. It's solely dependent on the rate of only one of the reactants. And it's first order because we're looking at these exponents, and for the order number, we're going to count up the exponents. We only have one exponent here, so this is first order. A second order reaction would be dependent, the rate is dependent on the concentration of A and the concentration of B. So we have an exponent here, 1, and an exponent here of 1, so that is a second order reaction. We have some third order reactions, and they are dependent on the concentration of A squared times the concentration of B. This gives us 2 plus 1, it gives us a third order reaction. Okay, so let's look at the things that are going to affect our rate constant. The first thing is going to be the energy of activation. Then we'll be talking about the temperature. And we'll talk also, well, actually we're not going to talk about it, we're just going to mention it here, that there will be steric considerations. This is the shape of the molecules, how easy it is for them to bump into each other in the right conformation. Okay, so let's first talk about the energy of activation. Here is our potential energy on this axis and our reaction coordinates here. Our reactants start here, and I've been drawing this for some time. There we go. Here's our reactants, and our products are down here. To get from reactants to products, the reactants need this much energy. I didn't draw a very straight line, but. And this is called the energy of activation. They have to climb that hill. It's the minimum energy required for a collision of the molecules to result in a reaction. Have to have that much energy in order to react. Only collisions with the required energy will form products. if we look at the average energy that the molecules have, these are the number of molecules on this axis, and this is the amount of energy those molecules have. Let's go to blue, and we will draw, kind of comes up, and then it will tail off. So this is any molecule and the energy distribution of those molecules. So at any given temperature, molecules have a distribution of energies. Only a certain number of molecules are going to have the amount of energy required, though. This is our energy of activation. And only these molecules are going to have the necessary energy to react. So if we have a small energy of activation, we'll have a faster rate. If my energy of activation, instead of being here, was down here somewhere, I'd have a larger percentage of molecules that are able to participate in the reaction. So I said we'd So we have reactants, products, and maybe do my green. Here's our energy of activation, and we have another reaction with a very small energy of activation. This one will be faster because the energy of activation is smaller. This one will be slow because the molecules have to gain this much energy before they can react. So let's look at the temperature. To hold the pen away. If I increase the temperature, I will increase the number of molecules that are able to participate in our reaction. So here's our energy of activation. If the temperature is the lower temperature, the blue temperature, we only have this small percentage that are able to react. If we shift the temperature, we will shift this curve of energies, and we have a much larger number of molecules that are able to participate. So raising the temperature increases the rate. There are also important steric considerations, the geometry of the reactants and collision orientation, which will affect rate, but we'll be talking about that later. Catalysts and enzymes will affect the rate. Note, let me draw the diagram here. We've got potential energy on this axis, and we've got the reaction coordinates here. We start with our reactants on this side, our products on this side, and this is our reaction curve. Okay, if I add a catalyst to this reaction, let's get a pretty color, we'll do orange. So the energy of activation is here. All right, if I add a catalyst, that will change this curve. And what it'll do is it'll lower, it lowers the activation energy. So a catalyst lowers the activation energy. It does not change the equilibrium. It does not change the energy of the reactants or products. It does not shift the equilibrium. All it does is increase the rate. It lowers the activation energy and it will increase the rate. Doesn't do anything else. Enzymes are used by biological systems as catalysts. Oh, I guess I also should tell you that catalysts are not consumed. So your body uses enzymes to lower the rate, to increase the rate by lowering the activation energy. Okay, and next we'll have reading energy diagrams.